Well, these detrital zircons, the mineral zircon, comes from these granitic rocks, and so the sedimentary rock that we find these detrital zircons in had to have come from an older rock, which is aged at about 4.4 billion years old. Now, the fun thing about that is that zircons are largely found in more felsic rocks, and so that may suggest something about the processes that were acting early on in Earth's history. Now, that's just sediment. Again, we can age date sediment within a sedimentary rock and kind of get a good idea um, from that, but the oldest rock itself is generally attributed to the Acosta gneiss, which is in northwest Canada, and it's thought to be about 4.03 billion years old. Now, when we're discussing um, dates and numbers this big, this large, it's really easy to trivialize it because, let's face it, when we're faced with a large number of anything, I mean, you go and you try to guess how many jelly beans are in a jar, and your mind only conceptualizes about 100 to 200 of them in there. There could be 400, 500. There could be an upwards to 1,000 if it's a big jar, 2,000. But it's very difficult for us to conceptualize things that are much larger than us or have a larger number in that sense. And so it does help to take a step back and look at the overall context of our story and of the Earth story to try to get a little better idea of the depth of time that we're really working with. And to do this, we can take a look at the place that we live in, the universe itself. When we look out in the night sky, really all we see, um, and if we're lucky, we might actually see beyond that, but all those points of lights, all those stars that you see up there, are points within your own galaxy. You have to have a fairly high-powered telescope or binoculars and the right time of year look at the horizon. You might see our next door neighbor, the Andromeda galaxy, but that really does not betray the overall size of the place that you live in. See, there are hundreds of thousands, literally billions upon billions of galaxies out there, all of which play host to billions upon billions of stars. Again, when you look up in the night sky, all those stars that are up there are within your own galaxy, and most of them you can't even see with the unaided eye. There are some 400 billion stars in our galaxy alone, and some of those play host to planets. Our own star plays host to us. And when we look at the atomic makeup, the chemical makeup even, of our bodies and of the things that we know and love and enjoy, it's largely those heavier elements that are born, that are made, that are fused in the furnaces at the very pits of these stars. And so when you look at yourself, you just look at your hand, and you realize that you yourself are made out of recycled star bits. That as the universe has gone on cycling and has produced supernova, galaxies from that, the particles that are being reborn and recycled, these things have ultimately come into you. And so hopefully that inspires you. If it doesn't, well then too bad. But that hopefully puts you into the right mood, if you will, or the right mind frame. Because when we look at the absolute depth of the history of the Earth, we're really working with a large amount of time. See, the Earth is about 4.6, 4.5 billion years old, and so it's hard for us to conceptualize it because we live only 70, 80, 90 years. Compare that to the immensity of the history of the Earth. Compare the overall history of humanity. even all the way back to the beginning of our species, some 300,000 years ago, and compare that with 4.6 billion years. It is humbling, to say the least. And so it's very difficult for us to conceptualize that, but we will try. So, this age date, this 4.6 to 4.5 billion years, your age date, largely, again, as we described earlier, it comes indirectly. But at the beginning, at this beginning point where the Earth is coalesced into this planetary body, the Earth itself is probably homogeneous, a uniform mixture of material. And as such, it probably has a uniform density. But when we look at the modern Earth, this modern planet, we see layers. We can look at the seismic data that comes back from particularly large earthquakes, and we're able to actually see some differentiation. The crust, the mantle, the core, and the even subdivisions of that. There are density differences, and there are essentially chemical differences, mineralogic differences between these layers. So how do you do that in a solid material? I mean, set your keys down on your desk. Do your keys sink through the wood? Of course not. The physics of it is that solids don't generally differentiate due to density. But what does? Liquids, like oil and water, they will separate. So what changes? How can we get from a solid material to a partially liquid and mostly solid layered planet? Well, we have to start melting those solids, those rocks that have coalesced. But where are we going to get the heat from? Well, the early solar system is a fairly crowded place, and so we can envision a ton of celestial impacts. When we look at the moon, we see tons of craters. When we look on Earth, we see a large handful of craters. Look elsewhere in the solar system, we see the same thing. So these celestial impacts have occurred, and in the early history of the Earth, probably occurred a lot more. And so it's a good exercise. Um, Open up your palm and close your fist of your other hand and smack them together. You generate heat from that impact. Now multiply that by hundreds of billions of times, and think about the heat that's generated by a meteorite impact. So that's one input of heat. Also, gravitational compression. Close your fists. Make a closed fist and squeeze. That squeezing is very much akin to gravitational compression. At the very pit of these planets, and especially the pit of the sun, a lot of gravitational compression results in heat. And not only that, but we know that the Earth is made up of a large variety of materials, some of which are radioactive. They have radioactive isotopes, and so they give off heat as they essentially decay. And so these three inputs of temperature increase allow for essentially the melting of the early Earth. And so we end up getting our layers from density differences that way. The iron, the heavy material, iron, nickel, even the gold that was originally on the planet is all now down into the core. It sifts to the center. The silicates form the mantle. There's a large variety of silicates. You can think of quartz as one, but also the iron rich or magnesium rich olivines are also another form of silicate. There's a wide variety of silicates, and they make up the majority of the mantle and the crust itself. And so the lighter or less dense silicates are what we see here close to the surface, and the more dense silicates are residing here in the mantle. And through time, as that differentiation, layering due to density differences, forms what we know and love today as the Earth. So when we look at the Archean crust, that initial material that's being formed from this, We know that the Earth is hot enough to melt the mantle. It's what's produced the layering effect. And the mantle melt is very rich in iron and magnesium still. And so those iron and magnesium rocks form what we know as mafic rocks. Remember all the way back into physical geology when you were categorizing igneous rocks into mafic, intermediate, and felsic. Mafic rocks contain those iron and magnesium rich minerals. The result of all this melting forms that magma ocean, which cools, which continues to cool. And it forms this crust of rock that is ultramafic, that contains very high temperature minerals. And this rock is what we call a komatiite, named after the first komatiites that we found in the Komati River in South Africa. Well, the cool thing about these komatiites is that we can look at the minerals that are inside this rock. We can look at the composition of it, and the composition suggests that the minerals started to crystallize at about 1600 degrees Celsius. That is ridiculously hot, even compared to some of the hottest temperatures that we're able to record today, which are coming out of essentially Hawaii's volcanic eruptions. Those basalts that are formed essentially from mantle melt there are only 1100 degrees Celsius. And so that suggests something about what's happened to the mantle from the Archean to present day. And that's essentially that it cooled. And so when we look back into the Archean, these processes, and especially the processes that we're going to be talking about in a little bit, the tectonics, there really isn't much of any modern analog that we can compare to. Remember, we talked about the principle of uniformitarianism, where the present is the key to the past. Well, if there's no modern analog that we can compare to, then really the present doesn't really help us figure out what's been happening in the past. And so we have to look towards essentially actualism, which is those natural forces, the processes that have been acting, if you will, are those that will continue to act. And so we can actually still look at the composition of these rocks. We can look at the structure of these rocks as they form and as they interact with Archean processes, and we can model what might be happening out there. And those models suggest that the tectonic motion is much different than what we see today. See, modern plate tectonics, we talk about plates moving essentially vertically, or not vertically, but laterally, side to side. Sure, there's some vertical motion, such as subduction and that, but largely it's this opening and closing of ocean basins that's producing the overall movement. So this is a nice lateral or horizontal movement that we see today. In the Archean, however, it's much more vertical and up and down motion. And this is because, again, and we'll talk about this a little bit later too, but the structure of these rocks, they're not rigid. And not only that, but these komatiites are much denser than the partly molten upper mantle of the time. And so those komatiites are going to sink. And this up and down motion essentially creates a scenario where that komatiitic rock is going to be partially melted. The lower temperature minerals will be reabsorbed back into the mantle and will essentially recycle. The entire rock's not going to melt, but part of it will. And in this case, what's being generated from this partial melt, this recycling, is a more felsic magma, a granitic magma, if we can use the term loosely.